Chapter 6 is the cardiovascular system and its control. As we talk about the cardiovascular system, the major functions of the cardiovascular system can be grouped into 6 categories. First, we have the delivery of oxygen and other nutrients. So the other nutrients could include, as we've talked about, glucose, FFA. It's also responsible for removing CO2 and other metabolic products like lactic acid. You'll also see that the cardiovascular system is in charge or in control of transporting hormones and other molecules. For instance, epi, norepi, insulin, glucagon. Those are some of the hormones we've talked about. It's responsible for thermoregulation. We've talked a little bit about that. We will talk more about that. The blood essentially absorbs the heat and carries it to the surface of the body where we can get rid of it. It's also responsible for the control of body fluid balance, which is in the chapter, but we will actually not talk about this one. It participates in acid-base balance, so that's the maintenance of normal pH. We've talked a little bit about that. We will be talking more about that in this chapter and the next chapter. And the regulation of immune function, which again is in the chapter, but we won't cover that. So the cardiovascular system is a circulatory system, and all circulatory systems have 3 components. We have a pump, and that's the heart, and the pump is connected to a system of channels, and that would be your arteries and your veins, which we'll talk more about. And all circulatory systems also have a fluid medium that moves through the channels, and the fluid is moved because of the action of the pump. So the fluid in the circulatory system of the heart would be the blood. So this is much like a circulatory system in a swimming pool or in a fish tank, where the pump, you've got an electric pump, and the water, which is the fluid medium, runs through that pump. And it is, in a fish tank, it would be some plastic tubing, and the water moves through the plastic tubing. The reason the water moves through the tubing is because of the action of the pump. Okay, it's the same thing with the heart. The heart is the actual pump. The channels are our blood vessels, and the fluid is our blood. So by the action of the pumping heart, the blood moves through the body. You can look at the anatomy. We're not going to go into a whole lot of anatomy of the heart. You need to know that it has 4 chambers. You've got up here, you've got the right atrium. We have the right ventricle. We have the left atrium, and we have the left ventricle. We also have these valves here. The valve that connects the right atrium to the right ventricle is called the tricuspid valve, and the valve that connects the left atrium to the left ventricle is called the mitral valve. I prefer just to call them AV valves. It's a generic term, AV meaning atrioventricular valve, so it's a valve that connects the atria to the ventricles. So it's important for you to understand the anatomy of the heart before we talk about the physiology. Another way that I like to look at the heart, a really simple diagram, would be, and you're going to see me draw this a lot. So here we have the heart, we have the right atrium, left atrium, right ventricle, left ventricle. Coming out of the left ventricle, we have the aorta, and going into the right atria, we have the vena cava. Okay, and then we've got our AV valves here. Okay, so very basic anatomy of the heart. Okay, together the pulmonary and systemic circulations are a closed loop system. So what we have here is a closed loop system where blood never leaves the system. It's just constantly circulated throughout the system. So if you trace blood flow, if we start here from the vena cava, the blood enters the right atrium through the vena cava, goes into the right ventricle after passing through the AV valve, leaves the right ventricle and the heart through the pulmonary arteries, and that carries the blood through the lungs, the capillaries of the lungs. And what happens in the lungs is that the blood picks up fresh oxygen, drops off CO2, comes back, leaves the lungs through the pulmonary veins. Okay, the blue here represents low oxygen, and the red represents high oxygen. So when the blood leaves the lungs, it's now high in oxygen because it's just picked up oxygen from the lungs. Okay, so it goes through the pulmonary vein, blood flow re-enters the heart in the left atrium, goes through the AV valve into the left ventricle, leaves the left ventricle, leaves the heart through the aorta, and from the aorta it branches out into all the arteries of the body, which branch into the capillaries. And in the capillaries is where we drop off oxygen. We're using oxygen in the cells. So these capillaries are going through all the cells of the body, and so we're going to lose oxygen as we go through the capillaries. We're going to pick up some CO2, and those capillaries are going to drop their blood into systemic veins, and those veins all end up in the vena cava, which end up in the right atria, and the whole process happens again. So you can think of the heart as two separate pumps. Okay, the right side of the heart is the pulmonary side. Okay, so the right side of the heart is responsible for pumping blood out of the heart and into the pulmonary system. And then the left side of the heart, we sometimes call that the systemic side, because when the left side of the heart contracts, it causes blood to leave the heart and to go out into the system. So two separate pumps, pumping blood to different parts of the body. Like I said, the blood leaving the heart from the right side is relatively low in oxygen and high in CO2, because this is the blood that has gone through all the cells in your body where we've taken out oxygen to use it, and picked up CO2, because in the process of using oxygen we produce CO2. And as the blood goes through the lungs, we lose the CO2, we gain some oxygen, so that when we head back to the heart through the pulmonary veins, we have a relatively high amount of oxygen and a relatively low amount of CO2. Okay, we don't drop off all of our CO2. There's still going to be some CO2 in the blood coming back to the heart, but it's relatively low. The driving force for the blood flow through this closed loop system is a pressure gradient. Okay, and we're going to talk a lot about pressure gradients this semester in multiple chapters, so this is a really important concept to understand, because you're going to see that it repeats in most, if not all, of the systems in the body. So basically, the reason that blood flows in the direction that it flows is because there's a pressure gradient driving the blood flow in that direction. So for instance, coming out of the left ventricle, we have the aorta. Okay, and the average pressure in the aorta at rest is about 100 millimeters of mercury. Okay, so it's a pressure. Millimeters of mercury are units of pressure, so it gives you an idea of how much pressure is in the aorta. We're going to call this pressure 1. Okay, And then as the blood flows through the body, through arteries, arterioles, capillaries, heads back to the heart, okay, by the time we get to the right atria, the pressure is essentially zero. Okay, and we're going to call this P2, pressure 2. Okay, and so you can see the blood is always flowing in this direction. You don't get backwards blood flow. Part of the reason it flows in this direction is because there's a pressure gradient pushing the blood in this direction. Okay, so blood always flows from high to low pressure. Okay, so if the pressures are different, okay, 100 here, 0 here, we have a pressure gradient. Okay, and the blood is going to flow from the high pressure to the low. And if we wanted to calculate the gradient, we would subtract the pressure where it's high from the pressure where it's low. In this case, that would be 100 minus 0, and therefore our pressure gradient would be 100 millimeters of mercury. So that is the pressure that is driving blood out away from the left ventricle, out into the body, and back towards the right atrium. All right, some more information here about pressure gradients. As I told you, blood flows in the body because of a pressure gradient. It's always going to flow down the gradient. In other words, it's always going to flow from high pressure to low, down the gradient. Blood also flows at a rate that's proportional to the gradient. So if you have a bigger gradient, the blood is going to flow faster. Smaller gradient, it's going to flow slower. To calculate the gradient, you just subtract the high pressure, which is P1, or I should say you subtract the low pressure, which is P2, from the high pressure, which is P1, and you can easily calculate the gradient. So for instance, we said that P1 is the pressure in the aorta, and it's 100 millimeters of mercury. Okay, and P2 in our example was the pressure in the right atrium, which was 0, okay, millimeters of mercury. Essentially no pressure in the right atria. So that's aorta. That's right atria, okay? And so the gradient is P1 minus P2. So in this case, the pressure gradient is 100. So that gives you an idea of how much pressure there is, and therefore the rate that blood flows. So if the gradient increases, okay, so if we wanted to increase this gradient, we would either need to increase P1 or decrease P2, okay? And what happens during exercise is that your blood pressure goes up. And so the pressure in the aorta goes up. So, for instance, your pressure in your aorta may go from 100 to 150 during exercise. Okay, so now P1 is 150. The pressure in the right atria doesn't change. Okay, so now we have a higher gradient. Okay, and with a higher gradient, we're going to get a greater flow rate. Okay, so blood flows at a rate proportional to the gradient. So if we want blood to flow faster, we need to increase the gradient. You increase the gradient, you increase the rate of blood flow. The same is true if we reduce the gradient. So if we're exercising and the pressure in the aorta is 150, and then we go to rest, okay, and then during recovery, the pressure in your aorta goes back down to 100, okay. Now we're back to a gradient of 100, okay, so now we've reduced the gradient, and therefore the blood is going to flow slower, which is okay, because now we're resting, we don't need blood to flow faster. So Now you know one of the purposes of an increase in blood pressure during exercise. If the blood pressure is increased, it's going to increase the pressure gradient and therefore increase the rate that blood flows to help you to deliver everything you need to deliver at a faster rate: glucose, FFA, hormones, oxygen, etc. All right, so the myocardium is the heart muscle. Myo is muscle, cardium is heart. So talk a little bit about the actual muscle of the heart. It's different than skeletal muscle. It's different than smooth muscle. So let's talk about it a little bit. So again, you've got 4 chambers in the heart. The left ventricle is one of the chambers. The left ventricle is really important because it has the most work to do. The left ventricle, when it ejects blood, it needs to eject blood out of the left ventricle, out through all the cells in the body. Okay, so it's got to push that blood out with a lot of force to move the blood all the way through the body and back to the heart. Okay, so it's the most powerful of the 4 chambers. It's the strongest chamber. Okay, and because of that, it's the thickest chamber. Okay, just like skeletal muscle, if you work the heart muscle, it will hypertrophy. It'll become thicker. So if you look at the 4 chambers, the left ventricle is going to be the thickest, most muscular chamber because it has to do the greatest amount of work. As far as fiber type of the heart, it's not exactly the same as skeletal muscle, but the fibers in the heart are very similar to type 1 fibers in skeletal muscle. They're highly oxidative, fatigue resistant, high capillary density, lots of mitochondria. Because as you can imagine, the heart doesn't get to rest. It needs to be able to contract for long periods of time without resting, and therefore it's going to get most of its ATP aerobically. The heart has its own set of arteries that feed it, okay, because remember that the heart is a muscle, and like any muscle, the muscle cells of the heart need to receive blood flow because the heart muscle needs to receive oxygen and glucose and FFA, and it needs to remove CO2, lactic acid, etc. I'll show you that on the next slide. The other thing is that the myocardium is stimulated involuntarily. So what that means is that you don't have to make a conscious decision to tell your heart to contract. Okay, the action potentials are going to come from the autonomic nervous system, and they're going to be involuntary signals telling the heart to contract. The other thing that's unique about the heart is that it also has intrinsic stimulation, which means that the action potentials can begin, or do begin, I should say, within the heart itself. Okay, so the heart generates its own action potentials, so you don't have to have the central nervous system tell the heart to contract. Okay, it contracts intrinsically on its own. Okay, the central nervous system has some extrinsic control over the heart. The central nervous system can change the rate of the heart, but the actual generation of action potentials that cause the contraction of the heart are generated from within the heart itself, and that's why we call it intrinsic stimulation. The slide here just shows you the coronary circulation. So these are the arteries that are not carrying blood flow through the heart, but carrying blood flow to the heart. So these are the arteries that are feeding the heart oxygen that it needs in order to produce aerobic ATP. All right, a little more information about the heart. As I said, the heart stimulates action potentials intrinsically and spontaneously. And so the pacemaker of the heart, okay, the location where action potentials originate is called the SA node. Okay, stands for sinoatrial node. So it's a group of cells that spontaneously develop action potentials and send action potentials through the conduction system of the heart. Okay, and just like with skeletal muscle, as the action potential travels through the heart, the cells in the heart contract. Okay, so the SA node is what we call the pacemaker. And if the SA node is left alone, if it doesn't receive any extrinsic input, it's always going to beat at 100 beats per minute. Okay. So we call sinus heart rate, intrinsic heart rate, 100 beats per minute. So if you don't tell this SA node to either slow down or speed up, it's automatically going to beat always at 100 beats per minute. And we'll talk about extrinsic control after this. Okay. We also have what's called the AV node, which is the backup pacemaker. Okay, your body has redundant and backup systems in case one system fails. So if the SA node does not generate an action potential, and this happens for a long enough period of time, the AV node will spontaneously send an action potential out through the heart. So it's the backup pacemaker in case the SA node fails. It's normal, the normal pacemaker of the heart is the SA node. We're not going to talk about EKG. Your book does go into EKG. If you go on to 446, you're going to get some more EKG, but I just thought I would show you this because it's interesting. So a normal EKG looks something like this, okay, and this is called a P wave. This is called the QRS, and this is called the T. Okay, notice that the P wave is upright. Okay, an upright P wave tells us that the pacemaker was the SA node. If you see an EKG like this, all right, okay, where the P wave is inverted, upside down, this tells us that the pacemaker was the AV node. So just by looking at someone's EKG, you know if the pacemaker is the SA node or the AV node. Okay, if the pacemaker is the AV node, then you know something must be wrong. If the pacemaker is the AV node, you know that something must be wrong with the SA node. So then that would cause the doctor to do some additional testing. Now the next thing we're going to talk about is extrinsic control of the heart. Okay, like I told you, normally if you leave the SA node alone, okay, so you've got your SA node up here, and if you don't connect any nerves to the heart and you just let the pacemaker do what it wants, it's going to beat 100 beats per minute. Okay, so 100 times per minute, it's going to spontaneously generate an action potential, and therefore the heart is going to contract 100 times per minute. Okay, but in reality, there are nerves connected to the heart. Okay, and that means that we do get some extrinsic control of the heart rate. Okay, so coming from outside of the heart, okay, coming from the CNS, we have impulses coming in the heart that are either going to tell the SA node to slow down. Okay, if it slows down, then the heart rate's going to be less than 100. Okay, so right now you're probably sitting, resting, fairly relaxed, and your heartbeat is under 100 beats per minute. Okay, that's telling you that the central nervous system is telling your SA node to slow down. Okay, when you exercise, your heart rate needs to go over 100 beats per minute. Okay, so we start to send action potentials to the heart from the CNS, telling the heart rate to increase. Okay, decrease or slow down, increase or speed up. Okay, and if the SA node is told to fire at a greater rate, it's going to go over 100 beats per minute, and that's going to happen with exercise. Okay, and we'll talk more about that.